because one of the problems is that I can give references, but then they may confuse you more, in the sense that it may take a long time to read them. Probably the word confuse is not correct no more anymore, but so that's why it's better if you just read the and I've given the definitions. Even still, if you want, then you can read it. But yeah, it's better that if you just use my definition and follow up, actually that's better, because yeah, that's how that's actually being how you become good in maths, right? You get a new definition and you start working with it. Yeah. All right. So let's talk about these things, Cauchy sequences. Correct. So how should I talk about Cauchy sequences? Do you? I hope I'm audible. Yeah. Do you people know what is topological space?
Yes.
Yes.
Yeah, you know the definitions. All right. So yeah, so maybe we will try to define Cauchy sequences in the Cauchy sequences in a topological setting. Okay. And then we might specialize. So yeah, there is a yeah. Then let me first say what I know. Then I'll. So let X be a set, okay, and tau be a. So I mean, of course, we all know the definition of Cauchy sequences. Okay. So now I will try to define Cauchy sequences without using the notion of distance. Okay. And try to see if it makes sense. All right. And of course, then you can also draw the analogy with the things you know already. So this is a topological space. Yeah, I will say it in. Yeah, so the notion of let's think about it, right? Cauchy sequences, what do they mean, right? They mean that they have a notion of distance, right? The definition, right? If you know the definition, they have a notion of distance, right? Something like this, right? And well, you see this distance. How do you say this? Look, if you have metric, then you can obviously generalize it to metric spaces. That's not a problem. But the question is, how do you generalize it to topological spaces? That way we can also understand what do open sets in a topology, how do they correspond and so on. So yeah, space. Yeah. So let's see if I fix a point. Yeah, is it so basically what is this? This says that the distance between xn and xm is less than epsilon, right? You see, this definition, it doesn't really tell you where is xm and where is xn, right? It just tells you the relative position of xn and xm, right? If you think about it, it tells you the relative position. So how do you capture that using open sets? Right? So tau, you see, tau is a collection of open sets. Tau is a collection of subsets, right? Is a collection of subsets which are open sets. I mean, those are like your nodes, those are like your barometers of distance, right? Different open sets are saying that, okay, these senses of closeness are allowed in the space, right? That's what they say. But using this, is it possible to capture the notion of I mean, relative closeness? That seems a little difficult, right? Certainly, you can just start with a sequence that you can do in a topology. That you can do. It's a set. X is a set, so you can have a sequence, right? But how do I say that this is Cauchy? That I actually don't know in a topological space. So so maybe I can say, let's see, given U in the topology means given an open set, U is an open set. This is what I'm saying. Given U, yeah, you would like to say that Xn and Xm are U close, but that doesn't make sense, right? Haha, it's much more complicated if I want to do. Okay, right. So I suppose it's difficult. I mean, it's not obvious. So what we'll do is something interesting. We will put a algebra structure on this topological space. Okay. So what we'll say is that X is a set with a binary operation. Okay. With a binary operation. Okay. Such that, so you're starting with this triplet, such that X comma tau is a topological space. Okay. Is a topological space. Okay. And X comma plus, or maybe I don't want to make you think that this is commutative. So just a dot. This is a group. So I mean, we want a way to shift things to the origin, right? This is what it is saying. So what is this? I mean, if you just look at this, what is this saying? That you have a notion of inverse, right? So you have this point xn and this point xm. You want to say that these become epsilon close, and for all n, for those are combinatorial data. But the point is, you want to say that xn and xm become close, right? So I mean, how do you say this? I should say, how do you say this in a relative way, right? Without having a fixed point? That's what being relative means. So if I want to say this in a relative way, I should say that xn minus xm is small, right? So basically, then they are saying that if you look at xn minus xm, so then what is that vector? I mean, if you imagine it like this, then this is that vector, right? And if you view that vector as a position vector, right? If you view it as at the origin, then it is this. If you fix one tail to be this, then the other is this. And you want to say that this is inside this epsilon ball, right? So what this is suggesting us is you should consider neighborhoods around the origin, right? And you should translate the data, translate the sequence to the origin, and then say that given any neighborhood around the origin, the sequence, the difference of the terms is eventually in that thing. Okay. And this we should write. Let's keep this picture. Should write. So x1, x2, dot, 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 yeah, is Cauchy if again, if given any u in tau, with what condition should be there on u? U is an open neighborhood. So here this is the epsilon ball containing the origin, right? Now it will have U is an open set containing the identity of the group, because this origin is the identity of R2, whatever. Right? This doesn't make sense in metric spaces. That's the downfall of this definition. If you want one definition which works for both metric spaces and this, then that you have to go to something called uniform spaces, but that requires a certain more language. So I'm not going into it. Okay. Yeah, this is easy. So I'm just saying it. This and the identity is there. So given such a neighborhood, given a neighborhood around the origin, right? There exists a n naught, okay, such that for all n comma m bigger than equal to n naught, okay. Now we want to say this, but how do you say xn minus xm? Well, now these are groups, right? Group elements. So you can just say xn xm inverse. Because this is xm inverse, right? Where the operation is of subtraction. So it's the same thing. This thing, this under the group operation, this thing. Now this just say that this is in U. That's all. Okay. So is this fine? You see that this definition, if this tau is replaced by usual topology, which means that you can then just take open balls of radius epsilon, varying the epsilon, and this dot is replaced by the usual addition in R2 or R or Rn, then this definition of Cauchy is same as your definition of Cauchy. Do you agree with this? Yes or?
Can I just explain the graph again?
Graph. Okay. Well, in the graph, you have xn and xm are 2 points in the sequence, right? You want to capture this thing that xn minus x, you want to say that xn and xm are relatively close, but you want to say that without alluding to a third point. That is what it means to say that they are relatively close. Yeah? So we should just take the difference and show that their difference is small. And so when you take the difference, it's this as a vector, it is this. If you treat those things as vectors, then as a vector, the difference is this. And it is small, its magnitude is small, so that's the same vector as this. And so you can just say that by saying that it xn minus xm lies inside this epsilon ball. Right? And this epsilon ball becomes my u, and it contains, and the epsilon ball is ball centered at the origin, that becomes my this condition, and this is just the usual condition. So is it okay? Right. Main thing I want you to notice is that you should see that this gives you that definition. Okay, but this definition is very powerful. This definition, you can start considering Cauchy sequences in group theory also and prove things using Cauchy sequence. Because, I mean, even suppose, for example, if you're reading Lie groups, then I mean, Lie groups are topological groups. These are called topological groups. I've not given the complete definition. Actually, it's a bad definition so far, but roughly speaking, there is no fault. It's fine. Idea is okay. Okay. So this is the situation, and let me just say a few of one or two more things. So number one is that, I mean, if you introduce an operation, group operation, and you introduce a topology, you have two things going around, then there has to be a connection between these two things, right? The point here is that if I want to say that xn and xm are close, right, then basically, I mean, let's say if you consider distances, say xn and xm are here in here, and these things are close. I want to ensure that I want to capture that they are close. But then I'm considering a completely new element, which is xn minus xm, or in group terms, I'm considering this element, right? And I'm saying that this is small. So you see, these two things being close and saying that this thing is small, right? So you see what I'm trying to say. Saying that these two things are close means this is small, means that this is small, and saying that this is small, this is sort of whatever, I mean, like this distance from your origin, if you want, that this is small. Yeah, I mean, this is based on the sort of uh, subconsciously we are assuming that the subtraction is good, right? That the subtraction is a continuous operation. You get my point, right? We are kind of saying, right, that close things move to close things, that if these two things are close, then these two things are close, means origin and this are close. But that is based on our assumption, and that may not happen in just a group, and because you can give any topology that doesn't connect with the group, right? So that to force that, we would want to say that this subtraction operation and this whatever, right, these operations are continuous, and so that is encoded in this thing. So I'll extend the definition here, and I will say that is a group such that this function from x cross s to x, right, which is just the group multiplication, right, is continuous. So a comma b going to ab, this is continuous. This is in the assumptions. It's continuous. And also another function, which is the inverse function, that is continuous. A going to A inverse, this are continuous. Okay, so that is in the definition. So all this data is called a topological group. It's called a topological group. Usually that X will be written by G to indicate that. Okay, and so along these lines, there are some homeworks. So homework number one, which is easy, is just to show that R with the usual topology and with the, I mean, yeah, topology, you can just think of it as, because it's a metric space, so there's no hardcore topology, it's easy. This is a topological group, right? Okay, I mean, this is where mathematics starts to happen in some way. What is that? Easier space. Okay. I mean, I suppose this is cleaner, right? I mean, so, but tell me, Sindhu, what is hard about it? That is the, I mean, yeah, you may say that it's abstract, but the point is that, see, when you try to prove, like, see, I'll tell you. So you look at this definition. That this is a topological space. So topology is something that you must know, right? And then this is, I'm just saying that something is a topological space and something is a group, right? Now that is just, I'm making a definition, and you have to just think of it as your usual what happens in R. You can think of it like that, right? And now when I'm defining this Cauchy sequences, this is just I mean, you can just think of it as a definition which is generalizing the usual definition, right? I mean, this is like a problem on its own. Like some definition is given, and then you work your way and prove things using it. That's all. I'm not asking you to prove any theorem, big theorem, right? And like this, now here is the practice. If you try to show that this is a topological group, then in that process, you're basically trying to show that this function from R to R, going to R, x comma y, going to x plus y is continuous. Like, what's wrong in doing that? That is completely, it's a concrete thing. I mean, this is how you practice the concrete things, or you revise or you mix the concrete things, right? That is my point. Otherwise, they are just isolated, and then you have to maybe try to remember them and so on. Okay, all right. Yeah. So that's my point. That the concrete things are embedded in this, and they are joined together, and then we are putting some words on that. Nothing more than that, right? I mean, knowledge of topological group is very, very useful. I mean, it won't be directly written that it's a topological group, but if you can see something as a topological group, then it's nice. This is how you, I mean, this is how you practice, right? I mean, because when you come to college maths, we don't really have tricky problems, right? We have theory that, and if you solve the theory, then if you solve the easy parts of the theory, then that's how you revise your easier things. And then it grows, right? Yeah. So you see, there is nothing wrong in this, I would say. Cauchy sequences are, yes. But you try to show this, yeah. And then I'll just give you one more question, but let me just check if it is correct. You see, the definition is new, but the concepts obviously is using the previous one. And when you check those concepts, then you basically end up revising. Okay. For this, you may have to revise. You may have to just go back and see the definitions of, yeah.
Can you have this definition of Cauchy sequence in the group where the operation is not multiplication, it's addition?
I have taken
X,
any,
X
no,
tau.
but this is for any operation, right?
Okay, it's not for multiplication.
No, that's a symbol. That's the power of the definition.
Okay,
It's
okay,
not just
okay.
fancy language, right? Yeah. Okay. All right. So I'll give the problem when I come back. These things are, this is actually the correct way to learn, and not to just sit and revise definitions. That's a bad way, I suppose. Anyways, we'll come back after 10 minutes and I'll give you 1 or 2 more questions, and then you try, okay, for homework. Yeah. Don't worry about